You ever steal a glance at the cosmos and feel, I don't know, a weird mix of being utterly tiny and yet strangely connected to something huge?
Oh, yeah, definitely.
You're not alone. Today, we're plunging into the deep end of the universe, aiming to grab some key understandings about its wild history and the rules that make it tick.
And we're doing it fast, sort of astrophysics at warp speed,
Yeah.
because let's be honest, who has endless time for dense textbooks?
Exactly. So what's the plan?
Our mission, let's call it, on this deep dive is to pull out the most mind-blowing nuggets about the universe, its incredible birth, the fundamental stuff it's made of.
And how we humans are trying to figure it all out, right?
Right. And we'll be drawing heavily from Neil deGrasse Tyson's Astrophysics for People in a Hurry. Think of it as your express lane to cosmic enlightenment.
Packed with wow moments, hopefully.
That's the idea. And maybe a few genuine surprises along the way.
Okay, let's do it. Rewind. All the way back. The very, very beginning.
Picture this. Absolutely everything, every star, every galaxy, you, me, crammed into a space smaller than a pinpoint.
Hard to even imagine.
Almost impossible.
Yeah.
Scorching hot, and all the forces of nature we know, gravity, electromagnetism, the nuclear force, they were all like fused together, unified,
A chaotic mess.
pretty much.
Yeah.
We still don't have the full picture, obviously. But this unbelievably tiny cosmos had only one way to go. Outwards. The Big Bang.
But our understanding kind of breaks down right there, doesn't it? Our best theories don't quite work together at that point.
Exactly. That's the huge challenge. Einstein's theory of general relativity, gravity, large-scale stuff, it clashes fundamentally with quantum mechanics, the physics of the super-small, the subatomic world.
So physicists are looking for a theory that bridges that gap.
That's the holy grail for a lot of them, yeah. A unified theory of quantum gravity. We're not there yet.
Okay, so stick with me here. The very first moment, it gets even weirder, right? The Planck era.
Oh, totally surreal.
Yeah.
We're talking the first tiny, tiny fraction of a second, from time zero up to about 10 to the power of minus 43 seconds.
Yeah.
It's
10 to the minus 43. I can't even process that. And the whole universe was how big then?
about 10 to the power of minus 35 meters across. Also ridiculously small.
So named after Max Planck.
Indeed. The German physicist, one of the founders of quantum theory. The conditions then were just so extreme, so off the charts, that our current laws of physics just stop working.
We're really guessing at that point.
It's a frontier, for sure. We're still sort of groping in the dark, that initial size. It's like comparing an atom to the whole observable universe, but even tinier.
Mind-bending. Okay, let's jump forward just a tiny bit. A trillionth of a second after the start. What's happening?
Still blisteringly hot. A swirling soup of fundamental particles and particles of light.
And photons have that weird wave particle thing going on.
They do. And get this. These photons were so energetic they could just spontaneously transform into pairs of matter and antimatter particles.
Pop into existence.
Pretty much.
Yeah.
And then, poof, they'd almost instantly annihilate each other, turning back into photons. A constant dance of creation and destruction.
Governed by EMC clock.
Exactly. That famous equation is key here. And it highlights the incredible energy locked up in even tiny amounts of matter because of that c squared, the speed of light squared. It's a massive number.
And antimatter that's real, not just Star Trek stuff.
Oh, absolutely real. Scientists discovered it way before science fiction writers latched onto it. It exists. We can make it in labs.
Wow. Okay, so this constant creation and annihilation, that sounds like it should just cancel everything out. How did anything survive?
You've hit on a huge cosmic mystery. It connects to the bigger story, this whole matter-antimatter dance.
Don't leave me hanging. You mean the asymmetry thing?
Precisely. The strong evidence points to a tiny, tiny imbalance in the very early universe. For every billion pairs of matter and antimatter particles, there was one extra particle of matter, just one.
1 in a billion. That seems insignificant.
It sounds it, doesn't it? But that tiny surplus was absolutely crucial. As the universe expanded and cooled, nearly all the matter and antimatter wiped each other out in a huge flash of energy.
Leaving behind?
Leaving behind mostly photons, yeah, but also that one lonely matter particle for every billion pairs that existed originally.
And that's the stuff that made everything. Stars, planets, us.
That's it, that tiny leftover fraction. Without that subtle asymmetry, the universe would basically be an empty bath of energy. No structure, no substance.
Okay, my mind is officially blown. Do we know why there was that asymmetry?
That's one of the billion-dollar questions. There are theories, ideas about processes in the early universe that might have slightly favored matter, but nothing's proven yet.
So we exist because of a cosmic rounding error, basically.
Wild.
Wild. Okay, universe keeps cooling. What's next?
Right. So around this time, you get about one electron frozen into existence for every proton. Then, as the temperature drops below 100 million degrees or so,
Still pretty hot.
oh yeah, but cool enough for protons to start fusing with other protons and neutrons. This is when the first atomic nuclei form. Sometimes called recombination, though it was the first time they combined.
Bit of a confusing name then.
Yeah, historical quirk. But the point is, stable nuclei are forming.
And what was the universe made of then? What was the basic recipe?
Overwhelmingly simple. About 90% hydrogen nuclei, 10% helium nuclei, plus just tiny traces of deuterium, tritium, and lithium.
And this all happened super fast.
Within the first 2 minutes after the Big Bang. 2 minutes.
Wow. From infinite density to basically hydrogen and helium soup in 2 minutes?
Yeah.
That's incredible. But hydrogen and helium alone don't make rocks or people.
Exactly right. They're the foundation. But you need more complex stuff for planets and life as we know it. The heavier elements, carbon, oxygen, iron, all that good stuff.
Where did they come from?
They're forged later, inside stars. Specifically, in the incredibly hot, high-pressure cores of massive stars, and during their explosive deaths, supernovae.
Stars are like cosmic element factories.
That's a great way to put it. They cook up heavier elements, and when the really big ones die, boom.
Supernova.
Right. And that explosion scatters those newly forged heavier elements across the galaxy, like seeding the clouds for the next generation.
Seeding the clouds with the ingredients for planets and maybe life?
Precisely. So fast forward about 9 billion years after the Big Bang. Lots of this stellar recycling has happened, and then in a pretty ordinary spot.
Not exactly the galactic capital.
Definitely not. Outskirts of the Virgo supercluster. In our Milky Way galaxy, which is a fairly standard spiral galaxy tucked away in the Orion Arm, an average star ignites.
Our sun.
Our sun, a relative latecomer in a quiet neighborhood.
But that cloud of gas and dust that formed the sun, it already had those heavier elements mixed in from previous stars.
Absolutely. Enough heavy elements to form not just the sun, but the whole system. Rocky inner planets, gas giants further out, asteroids, comets.
The works. But it wasn't smooth sailing at first, was it? The early solar system was pretty chaotic.
Extremely chaotic. For the first few 100 million years, it was like a cosmic shooting gallery. Leftover debris constantly slamming into the new planets.
Big impacts.
Huge high-speed impacts. Kept the surfaces of the rocky planets molten, basically. Not a great environment for complex molecules to form or stick around.
Sounds pretty brutal. But even those catastrophes, sometimes they lead to unexpected things later on.
They certainly can. Take the asteroid impact 65 million years ago, the one in the Yucatan Peninsula.
The dinosaur killer.
That's the one. Caused a global cataclysm, wiped out maybe 70% of all species on Earth, including, famously, the dinosaurs who had ruled for ages. A massive extinction event.
Terrible for the dinosaurs, obviously, but
Yeah,
good for our ancestors.
in a very strange long-term way, yes. Suddenly, all these ecological niches were empty. Our little shrew-like mammal ancestors, who had been mostly hiding and trying not to get eaten.
Had room to spread out.
Exactly. They diversified, evolved, eventually leading to primates and then much later to us, Homo sapiens.
Well-
Species that can actually sit here and talk about asteroid impacts and the Big Bang.
Talk about making lemonade from cosmic lemons. It's incredible. But it does bring up that big question again. What came before the Big Bang?
Yeah, that's the ultimate mystery, isn't it?
Yeah.
The honest answer is, astrophysicists don't know. We just don't know what, if anything, happened before that initial moment.
No clues at all.
Only highly speculative ideas.
Yeah.
Things that are really hard, maybe impossible to test.
Like what?
Well, there's the multiverse idea. Maybe our universe is just one bubble in a larger cosmic foam, with other universes constantly popping into existence.
Wrong.
Or maybe the universe just sprang from literally nothing due to some quantum fluctuation. Some even toss around the idea we're living in a giant computer simulation.
A simulation, like the Matrix.
Sort of, created by some super advanced civilization. But again, these are just ideas. Speculation, not established science.
So if someone asks, what about God? How does science handle that? Is that just outside the scope?
Pretty much. Science deals with what we can observe, measure, test. Ideas about a creator or a prime mover fall more into philosophy or theology. Science can explore how the universe began and evolved based on evidence. But the question of why there's something rather than nothing, or who might have initiated it, that's generally outside its domain right now.
Okay, so the ultimate origin story is still TBD. But once the universe got going, one thing seems solid. The laws of physics are the same everywhere. That's fundamental, right?
Absolutely fundamental. And remarkably, it holds up wherever we look. When scientists first looked closely at the light from our sun, breaking it down into a spectrum.
It's like a rainbow, but more detailed.
Exactly. They saw the same unique fingerprints of elements like hydrogen, iron, calcium that they saw in labs right here on Earth.
So the same atoms obeying the same rules millions of miles away.
Precisely. It showed the physical laws governing matter and light aren't just local rules, they're universal.
And didn't that lead to finding a new element first in the sun?
It did. A fantastic story. They saw spectral lines in the sun that didn't match any known element on Earth.
So they named it.
Helium, from helios, the Greek word for sun. Only later was helium actually found and isolated here on Earth. It's the only element discovered off-world first.
That's amazing. A little piece of the sun's identity, revealed before we found it under our own feet. It really drives home that universality.
It does, and it's why we can even contemplate searching for extraterrestrial intelligence or sending messages out like on the Pioneer and Voyager probes.
Right, the plaque and the golden record. With pictures, sounds of Earth, music.
Exactly. Human heartbeats, whale songs, music from Bach to Chuck Berry.
Didn't Saturday Night Live do a skit where aliens found the Voyager record and just sent back a message saying, send more Chuck Berry?
Yes, a classic.
Yeah.
It's funny, but it highlights the challenge. How do you communicate across potentially vast cultural and biological divides?
What would aliens even make of Chuck Berry?
Who knows? But the whole effort relies on this assumption that some basic science, maybe math, is universal. And crucially, that the fundamental constants of nature don't change.
Like Big G, the gravitational constant.
Exactly. Big G dictates how strong gravity is. If it had been different in the past, stars like our sun would have evolved very differently.
How do we know it hasn't changed?
Well, a star's brightness is super sensitive to the value of G. If G had changed significantly over billions of years, the sun's energy output would have fluctuated wildly.
And our geology and biology records don't show that.
Not at all. The evidence from rocks, fossils, climate history, it all points to a remarkably stable sun over vast timescales, which strongly implies G has been constant.
So the constants seem constant, the laws seem universal. That's pretty reassuring for scientists.
It's the bedrock, really. All our measurements suggest these fundamental rules apply everywhere and always have. And many things we see involve multiple laws working together.
Like that comet that hit Jupiter, Shoemaker-Levy 9.
Perfect example. To predict what would happen, the plumes, the scars in Jupiter's atmosphere, scientists needed models combining fluid mechanics, thermodynamics, orbital mechanics, kinematics, and gravity, all working together.
Even weather on Earth or storms on other planets.
Same deal. Earth's weather is complex, but it follows basic physics. Jupiter's Great Red Spot, that giant centuries-old storm, is driven by the same fundamental processes as hurricanes here.
It's a weird contrast, isn't it? These universal, unchanging physical laws versus, well, us. Human beliefs and actions seem so variable and unpredictable.
It's a stark contrast. Physics works whether you believe in it or not. Gravity doesn't care about opinions. Human affairs, well, it's a different story. But the laws themselves provide this constant underlying framework for the cosmos.
Okay, let's jump back to the early universe again. You said for the first, 380,000 years, it was like a dense fog, opaque.
That's right. Because it was still so hot and dense, it was filled with free-floating electrons and protons, not yet bound into neutral atoms.
And light couldn't travel far.
Exactly. Photons, light particles, were constantly bumping into these free electrons, scattering off in random directions, like trying to see through a really thick fog or the inside of the sun. Light couldn't travel freely across space.
So you couldn't see across the universe back then?
Nope. It would have just been a bright, uniform glow in every direction, but you couldn't see distant things.
But then something changed. It cleared up.
It did. As the universe expanded, it cooled. When the temperature dropped to about 3,000 Kelvin, roughly the surface temperature of a cool red star.
The electrons slowed down enough.
Right. Slow enough for the protons to capture them, forming stable neutral atoms of hydrogen and helium for the first time. This is that event called recombination.
The moment atoms formed. And that let the light travel.
Precisely. With most electrons now locked up inside atoms, the photons were suddenly free to stream across the universe without constantly scattering. They were decoupled from matter.
And that light from that moment is still traveling.
It is. That's the cosmic background radiation we were talking about. The light from the moment the universe became transparent.
The CMB. But it started out as visible light, right? Given the 3000 Kelvin temperature.
Yes, it would have been a bright yellowish-orange glow everywhere. But over the 13.8 billion years since then, the universe has expanded enormously.
Stretching the wavelengths of that light.
Exactly, stretching them way down,
Yeah.
from visible light through infrared,
Yeah.
all the way into the microwave part of the spectrum. That's why we call it the cosmic microwave background.
And it will keep stretching, eventually become radio waves.
In the very, very distant future, yes. We might talk about the cosmic radio wave background then.
It's like the universe's baby picture, faded and redshifted over billions of years. You mentioned it has a specific temperature profile, like a black body.
Right. Any object with a temperature emits radiation across the spectrum, but it peaks at a certain wavelength depending on how hot it is. Like an old incandescent bulb glows mostly in infrared heat, not visible light. The CMB has a near-perfect black body spectrum corresponding to its temperature.
And scientists actually predicted this temperature before it was found. That seems incredible.
It was an amazing piece of theoretical work in the 1940s. Gamow, Alpher, and Herman, they applied atomic physics to the early universe conditions and predicted we should see a background glow today with a temperature around 5 Kelvin.
5 Kelvin. And what's the actual measured temperature?
It's measured very precisely now at 2.725 Kelvin, so roughly 3 Kelvin.
Wow. They were off by less than a factor of 2, predicting the temperature of the universe billions of years later. That's just stunning.
It really is. Richard Gott's analogy nails it. Predicting a 5 Kelvin background is like predicting a 50-foot flying saucer will land on the White House lawn.
And finding?
And finding a 27-foot one actually showed up. It was an astonishingly successful prediction.
So who actually found it? Not the predictors themselves.
No, it was an accidental discovery, famously. Arno Penzias and Robert Wilson working at Bell Labs in the mid-60s. They were using a big microwave antenna for satellite communication.
And they kept getting this annoying background noise.
Exactly. A persistent hiss coming from all directions, day and night. They tried everything to get rid of it, even cleaned out pigeon droppings from the antenna, thinking that might be it. But the noise remained.
Meanwhile, just down the road.
Right. At Princeton University, a team led by Robert Dick was specifically building a detector to look for this predicted cosmic background radiation.
So when they heard about Penzias and Wilson's mystery noise,
They knew immediately what it had to be. The Princeton group realized Penzias and Wilson had stumbled onto the CMB.
wow, serendipity meets preparation. And Penzias and Wilson got the Nobel Prize for it.
They did, in 1978. And later, in 2006, John Mather and George Smoot won the Nobel for work with the COBE satellite, which mapped the CMB in incredible detail, including tiny temperature variations.
Turning cosmology into a precision science, you said.
Absolutely. Those detailed maps were revolutionary.
And looking at the CMB is literally looking back in time, right? Because light takes time to travel.
That's the key. We're seeing the universe as it was 380,000 years after the Big Bang, when that light was first set free.
So, if there were aliens in a galaxy far, far away looking back at our region of space, they'd see the CMB as slightly hotter because they're seeing an earlier version of it.
Precisely. They'd be looking back at a younger, hotter universe from their perspective.
So the CMB isn't just an old fossil, it tells us a lot about the universe's basic properties.
A huge amount. By studying the patterns in the CMB, those tiny temperature differences from place to place, the overall spectrum, combined with other observations,
We can figure out.
we can infer the strength of gravity back then, how quickly matter started clumping together, the total amount of ordinary matter, the amount of mysterious dark matter, and even the amount of dark energy.
Dark matter and dark energy, we'll have to get to those. But all that from this faint microwave glow.
Yep. And that information helps us figure out the geometry of the universe and whether it's likely to expand forever or maybe collapse again someday.
It really sounds like the discovery of the CMB was the turning point for cosmology.
It absolutely was. It took cosmology from something closer to mythology, honestly, into real testable science. And the detailed maps made it a modern precision science.
Even cosmologists with big egos have to bow to the data now.
Well, the data certainly constrains the theories. It provides firm ground truth.
Okay, let's zoom forward again. Let's talk galaxies. Our home, the Milky Way. Why Milky Way?
Comes from the appearance in a dark night sky. That faint, hazy band of light looked like spilled milk to the ancient Greeks. The word for milk was galaxias, which is where we get galaxy.
Makes sense. And we have neighbors.
We do. Our closest companions are the large and small Magellanic Clouds. They're smaller, irregular galaxies about 600,000 light years away.
Named after Magellan.
Yeah, his crew documented them during their voyage around the world. They're prominent in the southern hemisphere sky.
And the nearest big galaxy like ours?
That would be Andromeda. A beautiful spiral, a bit bigger than the Milky Way, about 2 million light years off. For a long time, before we knew it was a separate galaxy full of stars, it was just called the Great Nebula in Andromeda.
Nebula just meaning fuzzy patch back then.
Pretty much. These names all came before telescopes were powerful enough to resolve them into individual stars and reveal their true nature.
Now, I heard that these big, showy spiral galaxies like ours and Andromeda are actually kind of rare, that dwarf galaxies are much more common. You wrote an essay about this.
I did a long time ago. The Galaxy and the Seven Dwarfs. And yes, it's true. If you take any large volume of space, dwarf galaxies vastly outnumber the big spirals and ellipticals. Maybe 10 to 1, maybe more.
Why don't we hear more about them then?
They're just really hard to see. A big galaxy might have hundreds of billions of stars. A dwarf might only have a million or even fewer, so they're intrinsically faint.
Small, dim, and not very densely packed with stars.
Exactly. They often just look like tiny, boring smudges,
Right.
unless they happen to be actively forming stars. And even then, they're usually irregular blobs. Low surface brightness, easy to miss in surveys.
So maybe they're the normal galaxies, and we're the unusual giants.
That's a fair point. Our definition of normal might be biased by what's easiest to see.
And where do these dwarfs usually hang out?
Most of the ones we know best are satellites, orbiting larger galaxies like ours. The Magellanic Clouds are satellites of the Milky Way.
Is that a safe place to be, orbiting a giant?
Not always. It can be hazardous. Over long timescales, their orbits can decay due to gravitational interactions. The larger galaxies' gravity can stretch and pull them apart.
Galactic cannibalism.
That's exactly what we call it. The Milky Way is currently in the process of shredding and absorbing the Sagittarius dwarf galaxy. We see streams of its stars wrapping around us.
Brutal. What about when big galaxies collide with each other?
That happens too, especially in dense galaxy clusters. When large galaxies merge, it's a huge gravitational mess. Structures get warped, tidal tails of stars get slung out.
Does it trigger star formation?
Often, yes. The collision compresses gas clouds, triggering massive bursts of star formation. And sometimes whole stars or groups of stars get ejected completely into intergalactic space.
Stars just floating between galaxies. Can they form new dwarf galaxies?
Some might reassemble into small bound systems, new dwarfs. Others just become cosmic vagabonds, drifting alone in the void. We see evidence of past major collisions or mergers in maybe 10% of large galaxies, even more in crowded cluster environments.
How much of this galactic debris, these homeless stars, is out there between galaxies? Is it a lot?
That's a tough question to answer because individual stars are incredibly faint at intergalactic distances. But some observations of a very faint diffuse glow between galaxies and clusters suggest there might be as many homeless stars out there as there are stars inside the galaxies.
Really? That much?
It's possible. And adding to the puzzle, astronomers have found more than a dozen supernovae exploding stars detonating way out in intergalactic space, far from any visible host galaxy.
Which implies there must be unseen populations of stars out there where those supernovae originated?
Exactly. Since most supernova searches focus on known galaxies, finding them way out in the middle of nowhere suggests there's a population of stars we're otherwise missing.
So the universe is filled with not just galaxies, but also these vast clouds of gas, right? Hydrogen clouds.
Yes, everywhere. We know this primarily from looking at very distant objects called quasars.
Quasars are super bright galactic cores.
Right, and as their light travels billions of light years towards us, it passes through any clouds of gas lying in between.
And the gas absorbs specific wavelengths of light,
Yeah,
leaves a fingerprint.
precisely. We see absorption lines in the quasar spectra corresponding to hydrogen. And the farther away the quasar, the more intervening hydrogen clouds its light seems to have passed through.
Are these clouds just parts of normal galaxies along the line of sight?
Some are, yes, but most seem to represent a distinct population of objects, vast, primordial hydrogen clouds scattered throughout the universe, perhaps remnants from the galaxy formation process.
Okay, so we have galaxies, stars, gas clouds. But there's something else, isn't there? Something invisible that dominates. Dark matter.
Ah, yes, the big mystery. This story really starts back in the 1930s with an astronomer named Fritz Zwicky.
What did Zwicky do?
He was studying a huge collection of galaxies called the Coma Cluster. It's about 300 million light years away, contains maybe 1,000 galaxies.
And he measured how fast they were moving.
Yes. He looked at the galaxies orbiting the center of the cluster and found they were moving incredibly fast, Much faster than expected.
Faster implies more gravity holding them in orbit, right?
Exactly. Faster orbits mean you need a stronger gravitational pull to keep things bound together. Zwicky calculated the total mass the cluster must have to explain those high speeds.
And then he compared that to the mass he could actually see.
Right. He added up the estimated mass of all the visible stars and gas in the Coma cluster's galaxies. And the numbers didn't match. Not even close.
How far off was it?
Way off. The visible stuff accounted for only a small fraction of the mass needed to explain the galaxy's speeds. It looked like the cluster didn't have nearly enough gravity to hold itself together.
So the galaxy should have just flown apart billions of years ago.
According to the visible matter, yes. They were moving faster than the cluster's escape velocity. Yet the Coma cluster is clearly ancient and gravitationally bound.
So there had to be a huge amount of unseen mass providing the extra gravity.
That was Wiki's conclusion. He called it missing mass. Today, we call it dark matter.
Why dark matter? Does it mean it's dark colored?
Not necessarily dark-colored, but dark in the sense that it doesn't seem to interact with light. It doesn't shine, it doesn't absorb light, it doesn't reflect light. It's invisible to all our telescopes across the entire electromagnetic spectrum. We only know it's there because of its gravitational effects on the stuff we can see.
So it's not just missing. It's a fundamentally different kind of matter that we haven't identified yet.
That's the prevailing idea, yes. Some new kind of particle, or particles, that interact gravitationally but barely, if at all, in other ways. Finding out what dark matter actually is one of the biggest goals in physics and astronomy today. It makes up about 85% of all matter in the universe.
85%. Wow. Okay, that gravity connection brings us back to Einstein. His theory of general relativity is our best description of gravity, right?
Absolutely. Published back in 1916, it's been tested again and again and has passed every test with flying colors. It's an incredibly successful theory.
Including that recent detection of gravitational waves. That was predicted by Einstein.
It was a direct consequence of his theory. He predicted that massive accelerating objects would create ripples in the fabric of space-time itself, gravitational waves.
And we finally detected them in 2015, was it? From colliding black holes.
That's right. The LIGO Observatory made the first direct detection in 2015, announced in 2016. Ripples from two black holes merging about 1.3 billion light-years away.
1.3 billion years ago. While those waves were traveling towards us, life on Earth was evolving from simple organisms eventually into creatures that could build detectors to catch those exact waves. That's just poetic.
It really is mind-boggling when you think about the timescales. And Einstein's idea was radical. Newton thought of gravity as this mysterious action at a distance.
Spooky action, yeah.
But Einstein said, no, gravity isn't a force pulling things across space. It's the result of mass and energy warping the geometry of space-time around them. And then other objects follow those curves.
Like a bowling ball on a trampoline making a dent and a marble rolling nearby curves towards it.
That's the classic analogy. The physicist John Archibald Wheeler summed it up beautifully. Matter tells space how to curve. Space tells matter how to move.
Nice. So GR is our tool for understanding cosmic gravity. How do we measure the vast distances involved in cosmology?
We have a couple of main techniques. One relies on standard candles.
Objects with a known, consistent brightness.
Exactly. Certain types of exploding stars, type Ia supernovae, are thought to explode with roughly the same peak luminosity wherever they occur. So, by measuring how bright they appear to us, we can calculate how far away they must be. The dimmer they look, the farther away they are.
Makes sense. What's the other method?
The other relies on the expansion of the universe itself. Edwin Hubble discovered that galaxies are generally moving away from us, and the farther away they are, the faster they recede.
Hubble's law.
Right. So if you can measure a galaxy's recession speed, usually using the redshift of its light, you can estimate its distance using Hubble's law.
And do these two methods generally agree? The standard candles and the expansion speed?
They should, if our understanding is correct. If they started giving wildly different answers for the same objects, it would mean something's wrong. Either our understanding of supernova, or our understanding of cosmic expansion, or maybe even GR itself. So far, they agree reasonably well, but refining these measurements is crucial.
Okay, so we can measure distances. We know the universe is expanding.
Yep.
What about its overall shape? Is it flat, curved like a ball, or something else?
That's related to the total amount of stuff, matter, and energy in the universe. Cosmologists use a parameter called omega, written as A.
Omega, what does that represent?
It's the ratio of the universe's actual average density of matter and energy to a specific critical density. This critical density is the exact amount needed to just barely halt the universe's expansion over infinite time.
So how does omega relate to the shape?
If omega is less than 1, LM11, there isn't enough stuff, not enough gravity, to stop the expansion. The universe expands forever and has a negative curvature, like the surface of a saddle.
Okay. What if omega equals 1?
If omega 1, the density is exactly the critical density. The universe is geometrically flat, like a sheet of paper in the analogy, and expands forever. But the expansion rate approaches 0 over infinite time. It just barely avoids recollapsing.
And if omega is greater than 1?
If they're 1, there's more than enough mass energy. Gravity eventually wins, halts the expansion, and pulls everything back together in a big crunch. The universe has positive curvature, like the surface of a sphere.
So measuring omega tells us the ultimate fate and shape of the cosmos. Which one is it?
Well, here's where things got really interesting. Early versions of the Big Bang Theory, especially ideas involving cosmic inflation, strongly predicted that omega should be exactly 1, a flat universe.
Okay, so theorists wanted omega 1. What did observers find when they added up all the matter they could see?
That was the problem. When astronomers added up all the ordinary matter stars, gas, dust, and it only came to about 5% of the critical density, so omega was about 0.05, tiny.
But wait, what about dark matter? Didn't that help?
It helped, but not enough. Adding in the inferred amount of dark matter, which is about 5 or 6 times more abundant than ordinary matter, still only brought omega up to around 0.3, still well short of 1.
So theorists were saying omega must be 1, and observers were saying we can only find omega equal 0.3. That's a big disagreement.
A huge discrepancy. It was a major puzzle in cosmology for a while. Where was the missing two-thirds of the universe's required density?
And the answer turned out to be something completely unexpected.
Utterly unexpected. Dark energy. Observations, especially using those type Ia supernovae as standard candles, to measure cosmic expansion history very precisely in the late 1990s.
What did they show?
They show that the expansion of the universe isn't slowing down as you'd expect due to gravity. It's actually speeding up, accelerating.
Accelerating! What could possibly cause that? Gravity should be pulling things together, slowing it down.
Exactly. Something must be acting like an anti-gravity, pushing space itself apart. We call this mysterious influence dark energy. And the amazing thing is, when you calculate how much dark energy would be needed to explain this acceleration,
Let me guess. It's just the right amount to make up the difference.
bingo. Dark energy seems to account for about 70% of the universe's total mass energy budget. Add that to the 30% from ordinary matter and dark matter, and you get an
Omega 1. A flat universe, just like the theorists wanted, but filled mostly with stuff nobody had anticipated.
Precisely. Dark energy solved the missing density problem and explained the accelerating expansion in one go. But we still have very little idea what dark energy actually is. It's perhaps the biggest mystery in physics today.
So this dark energy is pushing everything apart faster and faster. What does that mean for the distant future?
It means that galaxies that aren't gravitationally bound to us in our local group of galaxies will recede from us at ever-increasing speeds.
Faster and faster
Until eventually they'll be receding faster than the speed of light. Not moving through space faster than light, which is impossible, but being carried away by the expansion of space itself at superluminal speeds.
So they'll effectively disappear. We won't be able to see them anymore.
Correct. Their light will never be able to reach us. They'll vanish beyond our cosmic horizon. Imagine looking out 1 trillion years from now.
What would future inhabitants of our galaxy see?
They might only see the stars within our own Milky Way galaxy, or whatever it merges into by then. All other galaxies would have receded beyond view, leaving just an endless dark void between the local stars.
That's chilling. They might not even know other galaxies ever existed.
It's a sobering thought. Dark energy could eventually erase the evidence of the larger universe, undermining future generations' ability to understand cosmology as we do today, unless we leave really good records, like a super long-lasting time capsule.
Wow, it gives you this recurring nightmare, as Tyson puts it, that maybe we're already missing fundamental pieces of the cosmic story, that maybe some crucial pages of the universe's history are already access denied to us.
It's a profound and slightly unnerving possibility, isn't it? What fundamental truths might lie just beyond our current observational or theoretical reach.
Okay, deep breaths. Let's shift gears slightly. Back to the elements. We said Big Bang made hydrogen, helium, tiny bit of lithium.
That's it. The first three.
And all the others, the carbon in us, the oxygen we breathe, the iron in our blood, they were all cooked up in stars and supernovae later.
Every single one. forged in stellar furnaces and explosions, enriching the gas clouds that formed later generations of stars, planets, and eventually life.
It makes the periodic table seem even more amazing. Not just a chemistry chart, but like a cosmic story.
Absolutely. Tyson calls it a cultural icon, representing this huge international scientific effort. And the elements themselves have such weird personalities when they combine, don't they?
Totally. Like sodium, a reactive poisonous metal, and chlorine, a poisonous gas. Put them together and you get table salt, NaCl, something we need to live.
Or hydrogen and oxygen, both flammable gases. Combine them, H0, and you get water, which puts out fires. Chemistry is wild.
So let's look at a few key elements from an astrophysicist's perspective. Start with the simplest, hydrogen.
Element number one, lightest, simplest, mostly made in the Big Bang. It's the most abundant element in the cosmos and in the human body, by atom count anyway.
And it does weird things under pressure, like inside Jupiter.
Yeah, under the immense pressure inside gas giants like Jupiter, hydrogen gets crushed so much it starts acting like a metal. It conducts electricity. This metallic hydrogen layer is thought to generate Jupiter's incredibly strong magnetic field.
Cool. Who discovered hydrogen?
Henry Cavendish gets the credit, back in the 1700s. He was a fascinating character, also famous for being the first person to accurately weigh the Earth, measuring its mass and density.
Okay, next, helium.
Number two, also mostly from the Big Bang, second lightest, second most abundant, and as we mentioned, the only element discovered first in the sun before being found on Earth.
Lithium.
Number three, the last of the Big Bang trio, but only made in trace amounts then. Most lithium around today was probably made by cosmic ray interactions or in certain types of stars.
Let's jump a bit. Sodium. Nah.
Sodium. Very reactive metal, explodes in water, not something you want to handle pure, but essential in salt. We see its yellow-orange glow in streetlights, right?
Yeah, those old low-pressure sodium lamps give everything that weird orange tint. Less common now with LEDs.
Much less common. The high-pressure ones were more yellow-white. Astronomers actually preferred the low-pressure ones because the light was concentrated in just a couple of wavelengths, easier to filter out. LEDs spread their light pollution more broadly.
Progress isn't always helpful for astronomy. Okay, iron, Fe, that's a big one, right?
Hugely important, cosmically speaking. Massive stars can fuse lighter elements together in their cores, creating heavier ones. Hydrogen to helium, helium to carbon, oxygen, silicon, all the way up to iron.
Why does it stop at iron?
Because iron has the most stable nucleus, or rather, the least energy per nuclear particle. Fusing elements lighter than iron releases energy, powering the star. Fusing elements heavier than iron actually requires energy input. Same for splitting iron via fission that also takes energy.
So when a massive star's core fills up with iron,
It's game over for fusion power. The core can no longer support itself against gravity. It collapses catastrophically, triggering the supernova explosion. Iron accumulation is the signal of a massive star's imminent death.
wow. Okay, a weird one. Technetium. Teeth.
Yeah, technetium is odd. Its name means artificial because all its isotopes are radioactive and decay relatively quickly. It's not found naturally on Earth. We make it in labs.
But it's found in stars. How?
That's the puzzle. It is found in the atmospheres of some types of old red giant stars. But its longest-lived isotope only has a half-life of a couple of million years. That's short compared to the star's age. So the technetium shouldn't still be there.
So the stars must be actively making it somehow, dredging it up from their cores.
That's the leading idea.
Better.
It implies processes are happening inside those stars that we're still trying to fully understand. It's a
Yeah.
cool astrophysical clue.
Last one for now. Iridium.
Dense stuff.
Incredibly dense. One of the densest elements known. A block 2 feet by 2 feet would weigh as much as a car. Makes a great paperweight, apparently. But it's famous for something else, right? The dinosaurs.
Exactly. Iridium is rare in Earth's crust because most of it sank to the core when the planet was molten. But it's much more common in certain types of asteroids.
And scientists found a layer of iridium right at the time the dinosaurs died out.
Precisely. All around the world, there's a thin layer of clay, marking the boundary between the Cretaceous and Paleogene periods, the KPG boundary, 65 million years ago. And that layer is enriched with iridium.
The smoking gun for the asteroid impact theory.
It was considered the smoking gun, yeah.
Yeah.
The idea is that a massive asteroid impact vaporized itself and huge amounts of crust, spreading this iridium-rich dust globally. It strongly supported the theory that an impact event caused the mass extinction.
Fascinating how these elements tell such different cosmic stories. Now, shifting focus slightly, shapes. Why are so many things in space? Round, planets, stars, moons mostly.
It's a great question. Apart from things like crystals or fractured rocks, and yeah, spheres dominate the cosmic landscape. And it boils down to simple physical laws, often favoring that shape.
It's the default shape.
In many situations, yes. It's often the starting assumption in physics thought experiments, the spherical cow idea would too. For liquids, it's surface tension.
Like soap bubbles.
Exactly. Surface tension tries to minimize the surface area for a given volume. And mathematically, the shape that does that is a sphere. If packaging companies could use spheres, they'd save billions on materials, but
Things would roll away. Impractical.
right. But for large cosmic objects, it's not surface tension, it's gravity.
Gravity pulls equally in all directions.
Towards the center of mass, yes.
Oh.
If an object is massive enough, its own gravity will overwhelm the structural strength of its material, like rock or ice, and pull it into a spherical shape. It's the lowest energy configuration.
So small things can stay lumpy, like asteroids or small moons?
That's correct. Objects with low mass have weak surface gravity. The chemical bonds holding their rock together are strong enough to resist gravity's pull and maintain irregular shapes. Think of Mars's moons, Phobos and Deimos. They look like lumpy potatoes.
Are there other ways things become non-spherical?
Sure. If a star, say, orbits too close to a massive companion like another star or a black hole, tidal forces can stretch it out. If it gets within the companion's Roche lobe, material can even be pulled off.
Creating weird shapes.
Yeah, sometimes elongated teardrop shapes, like a Hershey's kiss almost. Especially common in binary systems where one star swells up into a red giant.
What about rotation? Does spinning change the shape?
Definitely. Rotation creates an outward bulge at the equator due to centrifugal force and causes flattening at the poles. It makes objects into oblate spheroids.
It's like the Earth. It's not perfectly spherical.
So Earth bulges slightly at the equator. It's about 0.3% wider than it is tall pole to pole. Not much. But look at Saturn. It spins much faster.
And it looks noticeably flattened.
Yeah, Saturn is about 10% flatter pole to pole than it is wide at the equator. Very noticeable oblate spheroid. A prolate spheroid would be stretched pole to pole, like a hot dog bun versus a hamburger bun.
Okay, what's the most perfect sphere in the universe likely to be?
That probably goes to pulsars, neutron stars.
Those incredibly dense spinning remnants of supernovae.
Exactly. They pack the mass of the sun or more into a ball maybe the size of Manhattan.
Yeah.
The gravity is immense.
And they spin super fast.
Some spin hundreds, even close to 1,000 times per second. The centrifugal forces are enormous. If one spun much faster, say 4,500 times a second, its equator would be moving at the speed of light and it would fly apart.
So that puts a limit on their spin based on their size and density. What is their density like?
Unimaginable. A teaspoonful would outweigh Mount Everest. It's like crushing 100 million elephants into the size of a chapstick tube.
How is that even possible?
You have to crush atoms themselves. Gravity overcomes the forces holding atoms apart. Electrons get squeezed into protons, forming neutrons. It's basically a giant atomic nucleus.
So the surface gravity must be insane.
Mind-bogglingly strong. Even tiny bumps, mountains inches high, would represent huge amounts of stored energy and would likely be smoothed out instantly. Gravity just crushes everything flat.
Meaning pulsars should be the most perfect spheres nature makes.
That's the expectation, yes. Their intense gravity should overcome any tendency towards irregularity. Perfect little balls and neutrons.
What about shapes on the largest scales, like galaxy clusters? Do their shapes tell us anything?
They do. Clusters of galaxies often have very irregular shapes, raggedy structures, long filaments, vast sheets connecting denser knots.
Meaning they haven't settled down yet.
Exactly. It tells us they are often still in the process of forming and collapsing gravitationally. They haven't had time to relax into a more stable spherical equilibrium state. Some are so vast, the galaxies within them haven't even had time to cross from one side to the other within the age of the universe.
They likely formed in those elongated shapes.
That seems to be the case for the largest structures. They reflect the initial density fluctuations laid down shortly after the Big Bang.
You mentioned the multiverse earlier. Is there a version where universes are like separate bubbles?
Yes, that's one popular visualization. Multiple universes existing as distinct, non-interacting pockets within some larger space-time fabric, like ships at sea, potentially forever beyond each other's horizon. Still highly speculative, of course.
Okay, before we leave shapes, the spherical cow joke. You have to tell it.
A classic physics joke. Okay, so a dairy farmer is having trouble with milk production and calls in 3 experts: an animal husbandry specialist, an engineer, and an astrophysicist.
Okay.
The animal husbandry expert examines the cows, the feed, the environment, and says, You need to optimize their diet and living conditions. Makes sense.
Right, the engineer.
The engineer looks at the milking equipment and says, you need a more efficient, automated milking system. Also plausible.
And the astrophysicist.
The astrophysicist pulls out a notepad, scribbles for a moment, looks up and says, okay, first, assume a spherical cow.
Haha, because simplifying the problem to a sphere is the first instinct.
Exactly. It highlights the tendency in physics to simplify problems with idealized shapes like spheres to get basic insights, even if it ignores messy, real-world details. Sometimes useful, sometimes, well, you need more realism than a spherical cow.
Love it. Okay, let's talk light. But not just the light we see, invisible light.
Right, the electromagnetic spectrum. It started, in a way, with William Herschel back in 1800, the guy who discovered Uranus.
What did he do with light?
He was experimenting with sunlight and prisms, measuring the temperature of different colors of the rainbow, and he did what good scientists do. He included a control.
A thermometer placed outside the visible rainbow.
Exactly. He put one just beyond the red end of the spectrum where there was no visible light. And guess what?
It got hot. Hotter even than the visible colors.
It did. He realized there must be some form of invisible light carrying heat beyond the red. He called it calorific rays. We call it infrared radiation.
Wow. A control experiment leads to discovering a whole new kind of light.
Isn't that great? He literally wrote about discovering invisible light. Shortly after, others found another invisible light beyond the violet and ultraviolet.
So the visible spectrum, RYGBV, is just a tiny slice.
A sliver. The full electromagnetic spectrum stretches way out in both directions. In order of increasing energy and frequency, you have radio waves, microwaves, infrared, then our little visible window, red, orange, yellow, green, blue, indigo, violet, then ultraviolet, X-rays, and finally gamma rays.
And modern tech uses all of them, right? Radio, TV, microwaves, Wi-Fi, heat lamps, tanning beds, medical X-rays.
We've learned to exploit every single band. But it took astronomers a surprisingly long time to start looking at the universe in these invisible wavelengths.
Really? How long?
Well, infrared and ultraviolet were discovered around 1800. But it wasn't until the 1930s that anyone seriously built a telescope designed to detect invisible light from space, specifically radio waves. And systematic X-ray and gamma-ray astronomy came even later.
Why the delay? Over 130 years. We knew radio waves existed from Hertz in the late 1800s, X-rays from Röntgen.
Heinrich Hertz even showed light was just one part of this broader electromagnetic spectrum, which is why the unit of frequency is named a Hertz. Why the delay in astronomy? Probably a mix of factors.
Like what? Hubris. Thinking our eyes were good enough.
That might be part of it. Also, the technology needed to detect faint signals in these other bands, especially from space, took time to develop. For over 3 centuries, from Galileo up to Edwin Hubble really, telescope pretty much just meant an instrument for collecting visible light.
But now we realize how crucial it is to look across the whole spectrum.
Absolutely essential. A telescope fundamentally is just a tool to gather information from far away, augmenting our senses. Bigger telescopes let us see fainter things. Better optics give sharper images. More sensitive detectors capture light more efficiently.
And all the information from the universe comes to us as light.
Pretty much all of it travels to us on beams of light electromagnetic radiation. And crucially, cosmic events often emit light across multiple bands of the spectrum simultaneously.
So if you only look in visible light, you're missing part of the story.
You're missing huge parts. Think about a supernova again. The explosion itself generates intense X-rays, sometimes gamma rays and UV. We see the flash in visible light, obviously, and the expanding remnant, the nebula left behind, glows brightly in infrared and radio waves for thousands of years. The pulsar at the center might emit radio waves, X-rays, even gamma rays.
So to understand a supernova fully, you need telescopes tuned to all those different wavelengths.
Exactly. Without observing across the spectrum, we'd be fundamentally ignorant about many of the most energetic and important processes in the universe.
Okay, so who first deliberately pointed a scope at the sky to look for non-visible light? You said radio in the 1930s?
Yes, Carl Jansky, another Bell Labs guy. He wasn't even an astronomer. He was an engineer trying to track down sources of static that were interfering with transatlantic radio communications.
And he built a big, weird antenna.
Yeah, a rickety-looking thing that rotated, nicknamed Jansky's merry-go-round. He found a persistent, faint hiss that seemed to follow the stars, peaking once a day.
Not quite 24 hours, though, right? A sidereal day.
Exactly. The period matched Earth's rotation relative to the distant stars, not the sun. He correctly deduced the signal was coming from outside the solar system, strongest towards the center of the Milky Way.
What did he title his paper? Something dry.
Very matter of fact. Electrical disturbances, apparently of extraterrestrial origin. That was the birth of radio astronomy.
Did astronomers immediately jump on it?
Not really, it took a while.
Hmm.
The first person to build a dedicated radio telescope intentionally was an amateur enthusiast named Grote Reber, who built a dish antenna in his backyard in Illinois in the late 30s and made the first radio maps of the sky.
From his backyard. Amazing. And now radio telescopes are enormous.
Huge. Things like the early Jodrell Bank telescope in the UK, the first giant steerable dish, it even tracked Sputnik. That led to NASA's Deep Space Network. And now we have monsters like FAST in China.
Fast.
The 500-meter aperture spherical telescope, its dish is the size of 30 football fields, world's largest single dish.
Wow. And we also link dishes together, interferometers.
Right. Arrays, like the Very Large Array, VLA, in New Mexico, you've probably seen it in movies like Contact. Linking dishes electronically allows us to achieve incredibly high resolution, like having a telescope miles wide.
Even wider.
Oh yeah. The Very Long Baseline Array, VLBA, links radio telescopes across North America, from Hawaii to the Virgin Islands, creating effectively a continent-sized telescope with the sharpest vision in all of astronomy.
Incredible. Okay, what about the other end? The really high energy stuff. Gamma rays.
Gamma rays are the most energetic form of light.
Mhm.
Super high frequency, tiny wavelengths like the size of atomic nuclei. Discovered around 1900 in radioactive decay.
But hard to detect from space.
Very hard.
Hmm.
They weren't detected from space until a satellite called Explorer XI in 1961. The problem is gamma rays are so energetic they just punch right through normal mirrors and lenses. You can't focus them easily.
So how do you detect them?
Explorer AKA used a scintillator detector. When a gamma ray hits certain materials, it creates a cascade of charged particles that produce tiny flashes of light, which can be detected and their energy measured.
Yeah.
Modern gamma ray telescopes use similar principles, often involving large particle detectors.
Did gamma ray telescopes reveal anything unexpected?
Oh yeah. One big surprise came from NASA's Compton Gamma Ray Observatory in the 1990s. It detected frequent, intense bursts of gamma rays originating not from deep space, but from right here, near Earth's surface.
Gamma rays from Earth?
Yeah.
Like nuclear explosions?
That was the first worry. But no, these terrestrial gamma ray flashes, or TGFs, seem to emanate from the tops of thunderclouds, often just before a lightning strike.
What causes them?
The leading theory involves the incredibly strong electric fields inside thunderstorms, accelerating electrons to near the speed of light. When these super-energetic electrons slam into air molecules, they generate a burst of gamma rays. It's still an active area of research.
Wow. Thunderstorms creating gamma rays. Who knew? So we've really come a long way since Herschel noticed his thermometer warming up.
Absolutely. We've opened our eyes to the entire electromagnetic spectrum, allowing us to see the universe in its full, glorious, and sometimes violent complexity.
Okay, let's bring it back closer to home, our solar system. It seems packed, but it's mostly empty, isn't it?
Incredibly sparse. If you drew a sphere around Neptune's orbit, the volume occupied by the sun, all the planets, all their moons, it's something like 1/1,000,000th of the total volume inside that sphere.
1/1,000,000th. So what's filling the rest of the space?
Well, there's still stuff out there. Countless rocks and chunks of ice, asteroids and comets, dust particles, a constant stream of charged particles from the solar wind, and magnetic fields.
Mm-hmm.
But mostly, it's vacuum.
And even the big things, like our moon, have dramatic origin stories. It wasn't always there.
The leading theory now, the giant impact hypothesis, suggests the moon formed from a colossal collision early in Earth's history.
A collision with what?
Probably a Mars-sized protoplanet, sometimes nicknamed Theia, slammed into the young Earth. The impact would have been unimaginable.
And the moon formed from the debris.
That's the idea. The debris blasted out from Earth's outer layers, its crust and mantle, coalesced in orbit to form the moon. This explains why moon rocks, brought back by the Apollo missions, are chemically similar to Earth's mantle, but lack a large iron core like Earth has.
So the moon is mostly made of Earth's skin, essentially.
In a way, yes. And that early period of giant impacts wasn't unique to Earth. The whole inner solar system was getting pummeled. We see the scars preserved on airless bodies like the moon and Mercury.
Can those impacts knock rocks off planets and into space?
Definitely. Big impacts can easily eject rocks with enough speed to escape a planet's gravity. Computer models confirm it.
So there could be rocks from Mars, or even Earth, floating around space.
Absolutely. We've actually found meteorites here on Earth that chemical analysis proves came from Mars. About 1,000 tons of Martian rock is estimated to rain down on Earth every year.
We get rocks from Mars delivered for free. That's amazing. What about moon rocks?
Probably A similar amount comes from the moon. It's ironic we spent billions going to the moon to get rocks, and moon rocks are constantly coming to us.
Huh. Okay, beyond the planets we know, there's more stuff, right? The asteroid belt is between Mars and Jupiter.
Correct. Then beyond Neptune, there's another huge reservoir of icy bodies called the Kuiper Belt.
That's where Pluto lives.
Yes, Pluto is the most famous Kuiper Belt object, or KBO. There are many others, including objects called Plutinos, that have orbits similar to Pluto's, crossing Neptune's path. Some KBOs get perturbed inwards and become short-period comets, like Halley's Comet.
And even farther out.
Way, way farther out, perhaps halfway to the nearest stars, is a hypothesized, vast, spherical shell of trillions of icy bodies called the Oort cloud.
Spherical, not flat like the Kuiper belt.
Thought to be spherical, yes. This is believed to be the source of long-period comets, the ones that can come plunging into the inner solar system from any direction in the sky, not just the plane of the planets.
Like those really bright ones we saw in the 90s. Hale-Bopp and Hyakutake.
Exactly. Those were likely Oort cloud comets. They put on a great show but won't be back for thousands, maybe millions of years, if ever.
It's amazing how much stuff is out there orbiting the sun, and we use the gravity of these planets to navigate, right? Gravitational assists.
We do. It's a crucial technique for interplanetary missions. Spacecraft like Cassini, which went to Saturn, performed multiple flybys of planets like Venus, Earth, and Jupiter to steal a bit of their orbital energy and get speed boosts, like cosmic slingshots.
Saves a ton of fuel. Speaking of objects out there, didn't you get an asteroid named after you?
Haha, yes. Asteroid 13123 Tyson. It's out in the main belt. It's quite an honor, though lots of asteroids have familiar or sometimes quite whimsical names these days.
Okay, let's imagine we're looking back at Earth from space, say, from orbit. What human-made things could you actually see with the naked eye? The Great Wall.
The Great Wall is a persistent myth, unfortunately. From orbit, it's generally too narrow and blends in too much with the terrain. Maybe smoke plumes from large fires, like the Kuwait oil fires, possibly the World Trade Center site shortly after 9/11. Large-scale patterns like irrigated land versus desert, but individual buildings or structures, extremely difficult. The list is very short.
Mostly natural phenomena, then. Hurricanes, cloud patterns.
Those are much more obvious, yes.
Yeah.
Large geological features, coastlines.
Okay, now zoom out further. Imagine an alien civilization light years away, studying Earth with powerful telescopes. What might tip them off that this planet is interesting, maybe even inhabited?
First thing might be color. Earth would appear distinctly blue.
Because of the oceans. Water.
Exactly, that blue marble image. Water, HO, is actually the third most abundant molecule in the entire universe, after molecular hydrogen, HOs, and carbon monoxide, CO. So finding evidence of water wouldn't be shocking in itself.
But liquid water.
Ah, that's the key. The intricate shapes of our coastlines, the glint of sunlight off oceans, those would strongly suggest liquid water on the surface. And that implies a specific range of temperature and atmospheric pressure. Not too hot, not too cold, Goldilocks zone.
Could they see ice caps? Weather?
Probably. Seasonal changes in the size of the polar ice caps would be detectable in visible light over time, and our planet's 24-hour rotation would be obvious from watching continents and oceans spin into and out of view. Major weather systems, large cloud formations, would also be visible and distinguishable from permanent surface features.
But could they actually see Earth easily? Isn't it lost in the sun's glare?
That's the enormous challenge for direct imaging, especially in visible light. Earth is incredibly faint compared to the sun, billions of times fainter. It's like trying to spot a firefly buzzing right next to a blinding searchlight from miles away.
So they'd need incredibly advanced telescopes, or maybe look in different wavelengths.
Right. Earth actually shines relatively brighter compared to the sun in infrared light because of our planet's own heat, so looking in infrared might be easier. Or they might use other detection methods.
Like the transit method, watching Earth pass in front of the sun.
That's how we found thousands of exoplanets. If Earth's orbit lines up just right from their perspective, they'd see a tiny dip in the sun's brightness every 365 days as Earth transits across its face.
But that just tells them Earth exists and its size and orbit. Not much else, right? No surface details.
Correct. It reveals existence, size, orbital period, maybe hints about the atmosphere if they have superb instruments, but not continents or oceans directly.
So what would be a really obvious sign of, well, us, our technology?
Radio waves and microwaves. Earth is unnaturally extraordinarily loud at these wavelengths compared to a natural rocky planet.
All our broadcasts, TV, radio, radar, cell phones.
Everything. Military radar, airport navigation, satellite communications, GPS signals, even leaky microwave ovens. We are bathing our corner of space in artificial radio and microwave radiation.
Like a beacon saying someone's home.
Pretty much. A natural rocky planet emits very little at these frequencies. An alien civilization with technology like China's fast telescope could potentially detect this leakage, even from light years away.
Could they mistake it for something natural, like signals from Jupiter or the sun?
That's a possible complication. Jupiter is a strong natural radio source, and the sun emits radio waves too. They'd need to analyze the signals carefully to distinguish artificial patterns or narrowband transmissions from natural noise.
Okay, besides radio leakage, is there another way they could detect life or even technology by analyzing Earth's light? Spectroscopy.
Absolutely. Spectroscopy is incredibly powerful. Every element and molecule interacts with light in a unique way, absorbing, emitting, reflecting, or scattering specific wavelengths. These create unique chemical fingerprints in the light spectrum.
And our atmosphere leaves strong fingerprints.
Very strong. By analyzing the light reflected from Earth, or sunlight that passes through our atmosphere during a transit, aliens could identify the gases present.
And look for biomarkers, signs of life.
Exactly. Biomarkers could be biogenic, produced by life itself, anthropogenic, produced by human activity, or even technogenic, produced by technology.
Give me some examples. What might they see in Earth's spectrum?
Okay, maybe a strange nighttime surge in sodium emission. That could indicate widespread use of sodium vapor streetlights, a technosignature.
What about biological signs?
The big one is free oxygen. Oros makes up about 21% of our atmosphere. Oxygen is highly reactive. It wants to combine with other things. To maintain such a high level requires a constant, massive source.
Photosynthesis.
Yeah.
Plants and algae.
That's the dominant source on Earth.
Yeah.
So abundant free oxygen is considered a strong potential biosignature. Methane is another possibility, though it can also have non-biological sources, and some comes from human activity too. It's chemically unstable in an oxygen atmosphere, so its continued presence also implies a source.
So if they detected oxygen and methane together, that might be a really strong hint of life.
Potentially, yes. It suggests an atmosphere far from chemical equilibrium, possibly maintained by biological processes.
So aliens might first detect Earth's chemicals, infer life, and then maybe listen for radio signals to see if that life is intelligent.
That seems like a plausible chain of inference. Whether they start with chemistry or radio eavesdropping, finding evidence of advanced technology would strongly imply intelligent life is responsible.
It's humbling to think about being observed like that. It brings up the whole cosmic perspective idea. Who gets to even think about these things?
That's a really important point Tyson makes. Contemplating the cosmos is often a luxury. It's for people who have the time and resources beyond mere survival, living in societies that, at least to some extent, value intellectual curiosity and scientific exploration.
But there's a potential downside to that perspective, isn't there? A hidden cost.
Yes. Sometimes, gazing at the vastness of space and time can make earthly problems seem insignificant. It can lead to a kind of detachment, maybe even forgetting the very real and pressing issues right here: hunger, poverty, war, environmental damage, inequality.
We shouldn't let the stars blind us to the struggles on Earth.
Exactly. The cosmic perspective should expand our awareness, not numb our empathy or sense of responsibility. Tyson uses the analogy of an adult understanding a child's problems. Maybe humanity still has a collective immaturity, an ego-driven view that the world revolves around us.
Believing our group, our nation, our species is the center of everything.
Right. An expanded cosmic perspective, ideally, should help shrink those terrestrial conflicts, foster a greater sense of interconnectedness and tolerance, put our squabbles in perspective.
Some people worry that feeling small in the universe is depressing, though, like that psychology professor who was concerned about the Hayden Planetarium show.
Yeah, Tyson tells that story. The professor thought the Passport to the Universe show, which zooms out from Earth to the edge of the observable universe, would make people feel insignificant and depressed.
But that wasn't Tyson's experience, or mine when I see things like that.
Right. He felt the opposite: alive, connected, even large in a way. Large because our human minds, through science, are capable of grasping our place in this vast cosmos. That's empowering, not diminishing.
Maybe the professor's ego is the problem. Feeling small only hurts if you thought you were unduly big to begin with.
That's Tyson's take. If knowing your true scale makes you feel insignificant, maybe your sense of self-importance was inflated.
He mentioned a personal turning point, too, involving bacteria.
Haha, yes. Learning that the number of bacteria living in his own colon vastly outnumbers his own human cells, it prompted a rethink. Who's really in charge here?
Shifting from seeing humans as masters of the universe to participants.
Participants in a vast, interconnected web of life, linked across species, across billions of years of cosmic and biological evolution. It's a shift towards feeling connected, not just small.
And thinking about intelligence. The tiny genetic difference between us and chimpanzees leads to such a huge gap in abilities, apparently.
It makes you wonder, doesn't it? If that small genetic tweak makes such a difference, maybe our own intelligence isn't the absolute pinnacle we sometimes imagine it to be.
Could there be species out there whose intelligence dwarfs ours as much as ours dwarfs a chimp's, making our proudest achievements, like calculus, seem like child's play to them?
It's a humbling thought experiment. Maybe they teach multivariable calculus in their equivalent of preschool. It puts our own intellectual status in perspective.
And the sheer intimacy of existence here on Earth, like breathing the same air molecules that historical figures once breathed.
That's another powerful connector. The atoms that make us up have been recycled through stars, through the planet, through countless other living beings. There are more stars in the universe than grains of sand on all Earth's beaches, more stars than seconds that have passed since Earth formed, more stars than words ever spoken by humans. These comparisons ground us.
So the cosmic perspective offers, what, a sense of the past.
Definitely. Seeing distant objects is seeing back in time because of light travel. It also offers a deep connection through chemistry, knowing the elements of life were forged in stars.
And even the possibility of being Martians.
Panspermia.
That radical idea, yeah. That life might have originated on Mars when it was warmer and wetter, then got blasted to Earth on meteorites, seeding life here. If true, we are all descendants of Martians.
That would certainly change our self-image,
Mm-hmm.
which seems to be a recurring theme in astronomy, right? These cosmic demotions. It's a long history. First, realizing Earth isn't the center. Then the sun is just an ordinary star. Then our Milky Way is just one of billions of galaxies. Now, the multiverse idea suggests even our entire universe might not be unique.
Each step challenges our sense of being special or central.
Exactly. But the cosmic perspective isn't just about feeling small or demoted. It has positive attributes, too.
Like what?
It comes from science, but it really belongs to everyone. It's humbling. It can feel spiritual, connecting you to something larger without being religious in a traditional sense. It lets you grasp scales from the incredibly tiny to the unimaginably vast. It opens your mind.
But keeps it critical. Doesn't mean accepting woo-woo ideas.
Right. It encourages wonder but demands evidence.
So why keep exploring? Why keep pushing outwards with this perspective?
Because not being curious, not wanting to know our place, is like choosing to stay in a tiny provincial bubble. It's our duty, maybe, to ourselves and to future generations to keep exploring, partly for the sheer joy of discovery, but maybe more importantly.
To avoid falling back into those narrow, self-centered worldviews that breed conflict.
I think that's a big part of it. A cosmic perspective is maybe an antidote to the tribalism and arrogance that can lead us to harm each other and our planet. It encourages us to see the bigger picture, the shared journey on this fragile world.
Okay, we've covered a huge amount of ground, from the Big Bang to bacteria in our gut, all inspired by these amazing insights.
We really have. And honestly, we've only scratched the surface of what's in Tyson's book, let alone the universe itself.
It definitely leaves you thinking, reflecting on just how vast space and time are and how we fit into it all, or if we fit, in a way.
That sense of scale and our connection through atoms forged in stars. It's powerful stuff.
So maybe a final thought for everyone listening. Given this incredible journey the universe has taken and how our understanding keeps getting radically updated, what fundamental truths might we still be completely overlooking right now?
Ooh, that's a great cliffhanger. What seemingly impossible discoveries are waiting just around the corner, ready to rewrite our cosmic story yet again?
Makes you wonder, doesn't it?